Dear students, welcome to the video lecture series on Vocational Electronic Science. We are discussing the topic of AC fundamentals. This presentation is created and narrated by Hemant Satpute, teacher, Department of Electronic Science, Fergusson College, Junior Wing, Pune 4. In lecture number 21, under the topic of AC fundamentals, today we are going to discuss impedance of parallel resonance circuit, bandwidth of a resonance circuit, and a couple of numerical examples. So let's begin. Impedance of a parallel resonance circuit. The impedance at resonance for a parallel resonance circuit is maximum, and as we go off resonance the impedance drops. So here in the diagram it shows the graph of total impedance of the circuit against the frequency. So you will see that at resonant frequency the impedance is maximum, and that is given by as L upon CR. That is the formula. Now let's discuss bandwidth of a resonance circuit. Every resonance circuit has a property of discriminating between the frequency at resonance and those not at resonance. This discriminating property of the resonance circuit is expressed in terms of its bandwidth. The bandwidth of a circuit is the total number of frequencies below and above the resonant frequency that gives practically same response as at the resonant frequency itself. This band is also called as the pass band of the circuit. In case of series resonance circuit, the response can be seen in terms of the line current, and for a parallel resonance circuit in terms of its impedance. The frequency response of a resonance circuit, either series or parallel, is shown in the adjacent figure. The effective limits of the passband are taken at the points on the response curve corresponding to 70.7% of the peak value. The shaded area represents the band frequencies for which the circuit response is higher. So here is the frequency response for either series or parallel circuit. In case of series circuit, it is a graph of current against the frequency, and in case of parallel resonance circuit, it is the graph of impedance, total impedance of the circuit against the frequency. So here it shows that either current will be maximum or impedance will be maximum for series resonance circuit or parallel resonance circuit, whatever may be, as the case may be. Now this is the peak value of either current or impedance. If we consider 0.707 times the maximum value or peak value of either current or impedance, we consider the corresponding frequencies F1 and F2, and if we find the difference between F1 and F2, this difference is known as the bandwidth, and this shaded area represents the band of frequencies for which the circuit response is higher. Here F1 is known as the lower cutoff frequency and F2 is known as the upper cutoff frequency. I hope the things are clear. Now, since the quality factor Q of the circuit determines the overall steepness of the curve, the relation between bandwidth and the Q of the circuit is F2 minus F1, which is equal to bandwidth, and that is equal to Fr upon Q, resonant frequency upon Q. This formula shows that higher the Q, smaller is the bandwidth. Let's take a numerical example. A parallel resonance circuit has a capacitor of 100 picofarad in one branch and an inductance of 100 microhenry with a resistance of 10 ohm in parallel branch. If the supply voltage is 100 volt, calculate resonant frequency Fr, current through inductor IL, current through capacitor IC, line current, and impedance of resonance circuit at resonance. So let's see the solution. The resonant frequency is given by Fr is equal to 1 upon 2 pi under root LC. So let's substitute the values and simplify. We will be getting resonant frequency as 1590 kilohertz. Next, the inductive reactance, we have the formula XL is equal to 2 pi Fr into L. substitute the values, simplify, you will be getting inductive reactance XL is equal to 1000 ohms. R, value of resistance is 10 ohm. The resistance R is very small as compared to the inductive reactance XL. So the current in the inductive branch will be given by IL is equal to total voltage applied divided by the inductive reactance XL. So 100 upon 1000 ohm, that comes out to be 0.1 ampere. So this is the current flowing through inductor. Now capacitive reactance can be calculated by using the formula 1 upon 2 pi Fr into C. This is the capacitive reactance at resonant frequency. Substitute the values and we will be getting capacitive reactance Xc is equal to 1000 ohms at resonance frequency. Now current through capacitor IC is given by total applied voltage divided by capacitive reactance, that is 100 upon 1000, that comes out to be 0.1 ampere. Now the total impedance of the parallel circuit, Zp is equal to L upon R into C. So substitute all values and we will be getting it is 10 to the power 5 ohms. So impedance is maximum. Now the line current I will be given as total voltage divided by the impedance. So 100 upon 10 to the power 5, that comes out to be 1 milliampere. So I hope the things are clear. Only one thing, one word of caution, while attempting this, while writing the answer to such type of numericals in the exam, you have to write the answer in a following way. First write given, then write to find quantities, then write the formulas, then in each formula you substitute the given values and evaluate, and then finally write down all the answers with proper units in word. Let's take a second example. A tank circuit, it is also called as parallel resonance circuit, has a capacitor of 100 picofarad and an inductor of 150 microhenry. The series resistance is 15 ohm. Find the impedance, quality factor Q and the bandwidth of the resonance circuit. So here given the value of inductance 150 microhenry, value of capacitance 100 picofarad, value of resistance 15 ohm, parallel resonance circuit is given. We need to find out resonant frequency, impedance at resonance, quality factor Q and the bandwidth. So let's begin. We have the formula. Resonant frequency of tank circuit or parallel resonance circuit is given by Fr is equal to 1 upon 2 pi root LC. You have all the values, substitute, simplify, you will be getting resonant frequency equal to 1303 kilohertz. The impedance of the parallel resonance circuit at resonance is Zp is equal to L upon Cr, and that comes out to be equal to 10 to the power 5 ohm, which is also equal to 100 kilo ohm. So impedance is maximum, that is 100 kilo ohm. The quality factor Q is given by omega R L upon R, that is 2 pi Fr L upon R. Substitute all the values and you will be getting quality factor Q equal to 81.6. Now the bandwidth delta F is equal to Fr upon Q. We have resonant frequency Fr, we have value of Q. So substitute those and simplify, you will be getting bandwidth as 15.84 kilohertz. That's all for today's lecture. Stay tuned for next video in the series. Please do visit my YouTube video channel FYJC Vocational Electronics for all the video lectures on different topics in this series. Subscribe, like, comment, share and stay tuned.